to this session. I've been just appointed as the chairman of this session. Actually, I'm going to chair only the two first talks because I have to, my flight is around 5, so I have to leave here about 3. Well, it is a pleasure to introduce Cassio. Cassio has been working on these non-Newtonian fluids simulation. He is even more than a pleasure because he's been my former student and one of the most successful ones.
Oh, thank you.
So he's been working independently, made a career, and he's cooperating with Jonathan, of course, as you can see there. And Cassio did a PhD in USP in São Carlos, and after that he also did a postdoc in São Carlos, and he's been in this university, one of the centers of, one of the collaborative centers of CMI is in his university. So he's today talking to us this joint work with Jonathan, a numerical study of Oldroyd-B fluid in the natural stress formulation.
Okay.
Cassio.
Thank you, Poti. You have one. Okay. Oh, good afternoon. Thank you. I would like to thank André and Paul and Jonathan for this opportunity to present some results in non-Newtonian fluid mechanics. In particular, we have work in the simulation of complex flows and complex fluids. Okay. This is the outline of this talk. First, I would like to introduce our motivation in some application or CFD group of CMI. The leader is Professor Cominato. We have worked with moving free surface and interface problems, and in particular viscoelastic flows. After this, I would like to introduce some difficulties involving the numerical simulation of microflows using non-Newtonian fluid. I will comment two main problems in this type of simulation. And finally, we'll talk about one alternative strategy in order to improve the solution near to geometric singularity. This is I have a contribution of Professor Jonathan in this part of the work. Okay. I prepare one illustration about the difference of Newtonian and non-Newtonian flows. In the left, we have a Newtonian behavior. In the right, non-Newtonian. Here, the extrusion problems involving Newtonian and non-Newtonian observe some different behavior in this type of flows. This is the injection problem. We have studied some problems involve drops and bubbles. Note the difference in the shape when you move, we change the fluid involved in this simulation. This is the stretching of a filament. In the left, we have the Newtonian flow, and here we have one Oldroyd non-Newtonian fluid, viscoelastic fluid. This is formal problem called rod climbing. Jonathan commented about this in terms of experimental results. And the left, the Newtonian fluid, we have a rod dipping, not rod climbing. Okay, then this is the first part that we have worked in CMI, in particular in the CFD group. But more recently, we have turned our attention for viscoelastic microflows. We have some important application involving this type of fluid, for example, in medicine or in biofluids, in order to study some properties of biofluids. For example, the saliva is a non-Newtonian fluid, and then it's important to prepare some accurate and stable scheme for solving this type of problem. Other examples, we have interest to analyze the flow focusing device. Note the difference between a Newtonian and a non-Newtonian behavior in the same geometry. In particular, we note this is the micro channel, the scale used in this type of device. Here we have other interesting phenomenon. In the left, we have the Newtonian, and here we note one formation of a vortex near to the corner. Okay, and then our focus is to treat some elastic instabilities and to understand different types of transition or flow transition. I think it's possible to look in this map, the difference when you change the values using in these parameters, the Weisenberg and the Reynolds number. I will talk, or you comment some details about this. Other important problem in the extrusion industry is about the instability in the surface of the fluid. We have some phenomena like shark skin or the stick slip and other problems involving the extrusion. Well, then we are working with this type of application and problem. The governing equation, we are dealing with the Navier-Stokes equations, the momentum equation, and the mass, the conservation of the mass. It's important to comment about two terms. First is, okay, this is the contribution of the non-Newtonian extra stress tensor. And we have this parameter. Beta is defined as the ratio of the solvent viscosity and the total viscosity. This is important because when you have beta near to 0, we have more elastic influence in the flow. When you have beta equal 1 or near to 1, we have a more Newtonian behavior in the simulation. Reynolds number is the relation between inertia and visco force. Okay, when you are working with non-Newtonian flows, in particular viscoelastic problem, we needed to introduce one constitutive equation. And here we are working with this model called Oldroyd-B model. This is more famous model in terms of analytical solution. And then we first used this to introduce the numerical schemes. And note that we have this tensor called conformation tensor. And then this is the constitutive equation. It's possible to recouple the values of the extra stress tensor if you have the conformation tensor. Jonathan talking about this, a different type of the decomposition of this tensor. When we are using this decomposition 5, and then we call this formulation the Cartesian stress formulation. Well, note that for microchannels involved in that application, we have simple geometry. In particular, we have channels, then microchannels involved in this geometry. But we have the presence of the sharp corner, and this is a second problem that I will comment on. The first problem in terms of numerical simulation it's called high Weisenberg number problem. When we try to use a high level of elasticity in this type of geometry, we suffer some breaking downs in the codes. Okay, but what is the Weisenberg number? First, the first question is, what is this number? Well, we can define the Weisenberg number as the ratio between the elastic and visco force. And then this problem called high Weisenberg number was first presented in terms of a breakdown of the numerical scheme, independent of the type of scheme, finite difference or finite volume or finite element. In particular, when we have geometric corners or some stagnation point in the flow, the codes suffer some instability during the simulation, the transient simulation. Well, but some details about the conformation tensor. We can define this tensor as a 2x2 matrix if you are considering two-dimensional case, or 3x3. This matrix is symmetric, positive, definite, and then when you try to solve in this equation, we needed to preserve the positivity of this tensor. The solution for the high Weissenberg number problem is the inclusion of stabilization scheme in the code. We have many options for this. I think the famous method was proposed in 2004 by Fatal and Kupferman, and then we use a type of log decomposition in the matrix A. There are other options, but I think this is the most famous implemented in the codes, in the commercial codes nowadays. Using this type of stabilization scheme, we can capture some interesting phenomena like the formation of the corner vortex. We have in the left Weissenberg equal 1, in the right Weissenberg equal 4, but note that it's possible to capture this behavior observed in some experimental results. Well, then the first problem involving this simple geometry, we can bypass using some type of stabilization scheme. So now we are working with this problem involving sharp corners. Note that in the contraction flow, we have the corner, the sharper corner, and in particular near to this point, near to the corner, we note a type of degradation in the numeric solution. Then this is a problem in recent method, but researchers are using one strategy to capture a good result in terms of the extra stress tensor. The strategy is used a very refined mesh. Note that this is zoom near to the corner, and then we use a type of stretching. Or you can use a partition of the grid. But of course, this is not so cheaper in terms of the CPU time, because you need to prepare the grid, you need to prepare the code for dealing with this situation. Then, nowadays we are trying to understand some strategy, or this, in particular this strategy, to improve the solution exactly near to the corner. Then we are working with the natural stress formulation. Jonathan commented about this decomposition in his talk. And then we are using a dyadic decomposition in the conformation tensor A. And the idea is to use this decomposition, but using a relatively coarse mesh, not exactly refined, a highly refined mesh. Okay, this is the composition used now. Note that we have V and W, but here we haven't one detail about this. I will comment in terms of the regularization for using this scheme. It's important to say that when you use this decomposition, we need to create new equations for these parameters, lambda, mu, and nu. We are calling these the natural stress variables. This decomposition was first presented by Michael Renard in '94, but to our knowledge, he did not check or try check this formulation for transient problems. And then we decided to investigate what is the problem about this. And then, of course, in this paper, Renard proposed this decomposition using some ideas in terms of unsteady problems. Okay, to construct the equation for lambda, mu, and nu, we first apply this decomposition and the constitutive equation, and then after some manipulation, we can produce this new equation. And now we need to treat or to discretize this equation. Here we are using a type of scaling in the parameter involved in this formulation. Well, we can obtain or we can update the values of the extra stress tensor using this relationship between the extra stress tensor and the new variables involved in the natural stress formulation. In terms of numerical computation involved in this simulation, we have two main procedures. First, we needed to solve the Navier-Stokes equation. And after this, we needed to decide if we're using the natural stress or the Cartesian. But in summary, we first solved the Navier-Stokes equation using a type of projection scheme for uncouple the solution or uncouple the system, because we have the velocity and the pressure in the same equation. And then we needed to treat this coupled system. After this, we need to treat the constitutive equation using for the natural stress variable, or if you are using the Cartesian, then we solve directly the conformation tensor. One important thing in terms of numerical computation in this new formulation is the treatment of these terms. And then we are using a type of regularization. Well, this is given by this equation. Just depend on the problem, we needed to include you plus this term called the tolerance of the formulation. Delta is now then the tolerance. For example, for lambda hat equation, we add this tolerance in some terms involving the equations. But what is the difference? In summary, if you are using the Cartesian, the standard formulation, we solve these two equations. And if you decided to use the natural stress, now we needed to solve these three equations, and after this, compute the values of the extra stress tensor. Well, first I would like to show results in a verification using an analytical solution proposed in 2008. This is the two-dimensional channel, and then we are comparing our code or numeric solution of our code with this analytical solution. First, we have here one cross-section in the channel, and then we compare analytical and numerical. Note from this figure, we have one excellent agreement between numerical and analytical solution, varying the time involved in the simulation. Okay, here we have the same profile, but now not the same, exactly the same, but in the same point. But now we are checking the behavior of tau 11. This is the component the first component in the extra stress tensor, varying the values of beta and compare with the analytical solution. Again, we have a good agreement between numerical and analytical solution. Okay, but this is the I think is more important thing about the new formulation. We have studied this formulation in a contraction flow. We have two channels, and here we have a contraction. And we compare these new results with old formulation implemented in 2012, and using two uniform meshes. I am using M1 and M2 to denote these meshes. For example, one important thing is the influence of the tolerance in this new formulation. In red, we have plotted the solution using the Cartesian. But note that if you increase the value of the tolerance, we have a type of deviation in the solution. Where we are analyzing this result, we are analyzing this in a cross-section in the half of the first channel. And then when we are walking in direction of the wall boundary, note that this deviation in the result. And then we can conclude that it's very important to analyze the influence of the tolerance involved in this new formulation. For example, for using 10 minus 3, we have a bad result in comparison with the Cartesian results. Okay, this is the results for tau 12 is the shear component of the extra stress tensor. Again, note that near to the wall, it's important to reduce the values of tolerance, just remember the tolerance is involved in equations for lambda hat, mi hat, and nu hat. And then it's very important to check the influence of delta in this simulation. Okay, now we can discussion about the results near to the corner. First we have compare our results with the Cartesian. After this, we have one important solution proposed by Hint in 8.8 about the behavior of the stress near to this region. Okay, R is the radial distance from the corner to the point A, where we analyze the numerical solution. Okay, so I think Jonathan commented with more detail about the solution proposed by Hinton, and after this paper, other research, including Jonathan, proposed other solutions using asymptotic analysis. Okay, but it's important to verify the potential of this new formulation, comparing the results with the Hint solution. Using the M1 mesh, the values of R is 0.03, while for M2, we reduce the values of R. In this table, we include the results of Cartesian and the natural stress formulation in two different mesh. First, using the Reynolds number 0.05 and Reynolds number equal 1. What is important is because in the first case, we are using the creeping flow conditions. In the second, we are analyzing the influence of the inertia in this simulation. We include the values obtained in the approximation of Hint. Of course, we have one important discussion about the analytical solution and the numerical solution, but what is better in comparison with Hint solution. Note that using the Cartesian, we have the values of the extra stress, or the component tau 1 near to 2, while using this new formulation almost 12. If we refine, then we can note the potential of the natural stress formulation because we can obtain a value almost 20. There is a difference between the analytical and this numerical solution, of course, because in the analytical solution, some simplification are considered and other constant are included to analyze. And then nowadays we are working in this in order to verify if the solution using in this new formulation in the solution is in agreement with the solution proposed by Hint. But what is the advantage in implementing in our code the natural stress formulation? Here we have a good example to analyze the advantage because I am plotting here a variation of the extra stress tensor in the time. Then this is transient results for tau 1, exactly near to the corner. Then remember that in this sketch, we have this distance, okay? And then we are plotting the numerical results in point A and comparing the natural stress formulation using two curves mesh and the Cartesian using a very refined mesh. Note that the difference of the M2 in natural stress, we are using space step almost 10 times that the Cartesian, okay? And then it's possible to check the potential of the natural stress formulation because using a coarse mesh, we have result in almost 20, while using the Cartesian, considering the very fine mesh, the values of the stress is almost to 18, about 18. Okay, the discussion in terms of regularization. Here I have plotted again the variation of delta and comparing results with the Cartesian. note that if you reduce the values of delta, we can obtain better results in comparison of large values for this tolerance. Again, it's very important to check this, but we have noted that for 10 minus 6 or 10 minus 5, results are similar. It is a green and blue curves. Finally, we compare it. In the contractional flow, we have a type of corner vortex formed here in this region. And then now we compare our results obtained by natural stress formulation with some results proposed in the literature where we compute the reattachment length of the corner vortex. And note that the values obtained by Cartesian and natural stress formulation are in agreement with that obtained in the literature. Well, okay, then we have some observation about the contraction flow, just analyze the contraction flow. First, it's important to say that if you are using the natural stress formulation, it's important to include a small value for the tolerance in order to obtain good results in comparison with the Cartesian problem or Cartesian formulation. But in particular for M2, the stress peak obtained by the natural stress formulation is about 10 times greater than that obtained in the Cartesian. And comparing with the hint solution, was possible to observe that good results in terms of using a curse mesh. We are working in this, I just present some preliminary results because we are working with this formulation in order to understand. Nowadays we have some problems in terms of the variation of the geometry, other problems involved in the micro, or not only in the micro, but in different types of geometry. And then we are working in this direction to try to improve the solution of the natural stress formulation, but first results are indicating that this formulation is very efficient if you are dealing with corner or if you're a sharp corner in particular. Okay, this is the one alternative formulation. We are using in the mark and sell methodology to implement this scheme. This is the first time that we have obtained a result for transient problem. And nowadays we are analyzing this situation when you have a creeping flow, the Reynolds number is very, very small. When beta is equal or going to 0, when we have elastic a very strong elastic influence in the problem, and the Weisenberg number is high. Okay, I will conclude here. Thank you for your patience.